Hello, this is Brother Tony, and greetings from Bethlehem, here and right before Christmas in the Holy Land. And what am I doing? I'm actually recording a lecture for you. Now, we've gone through all that you need to know, or all there just about is to know about quadratic and linear functions, and now we're going to use them as mathematical models. So please take notes, write down everything in this video, and replay this what you don't understand. So the objectives: let's determine if the data is linear or nonlinear. Number two, be able to use a quadratic or linear function as a mathematical model for a real-world situation, depending on which is called for. Okay, so let's begin. Number one, determine if the data is linear or nonlinear. So how do we do this? Very easy. We calculate the slopes. We have 3 points. We calculate the slopes between those 3 points. So here in the green, right there, these 2 points. And what I do, I calculated the slope and got a -1. I took these 2 points, and really you can take 2 sets of points and calculate the slope. And so -1 does not equal 1. So what we know is the slope is nonlinear. Do we know that it's quadratic? No, we do not. But for these assumptions, the questions that are being asked in mathematical models that we will work with are either linear or quadratic. Now, how would we know if it's something else? And the answer to that is you'd have to plot the data. And what you would do then is you'd actually look at it, eyeball it up, and say this looks approximately linear, or this looks perhaps logarithmic, it looks natural log, etc. So we'll get to that later on, but all you need to know is it linear or nonlinear. Okay, so the second objective, be able to use a quadratic or linear function as a mathematical model for a real-world situation, depending on what's called for. So here we have the problem. An old Pizza Inn menu from the 1960s lists the following prices for a plain cheese pizza. Okay, so what is our dependent variable? P, the price in cents. We don't like dealing with decimals, so let's just make everything cents. The independent variable then is the diameter of the pizza in inches. So here we have our 3 points. For an 8-inch pizza, you pay 85 cents. 10-inch pizza, 115 cents. 13-inch pizza, 175 cents. Now the first question is the data linear or nonlinear? So what do? The green, I calculate the slope between the first 2 points. The red, I calculate the slope between the second 2 points. Is this linear or nonlinear? It's nonlinear because the slopes between the 2 points are not the same. So what do? We have to create a quadratic equation. So the second part then is, now that we know that it's a quadratic equation, how do we create the 3 equations and then find the general equation of the line? So we know that y equals ax squared plus bx plus c. Let me take you through the first point. So if x, or the independent variable, is 8, so this would be 64a plus 8b plus c equals 85. Now why don't you figure out the second 2 points, and then we can continue on once you're done. Try that now. Okay, so this is what I got, my 3 equations. So what do? I put it in good grapher and get the general equation for this pizza problem. So the price in cents equals the diameter squared minus 3 times the diameter plus 45. That's our general equation. For B, if Pizza Inn had made 20-inch pizzas, what do you predict the price of a 20-inch pizza to be? Well, we know how to do that by now. Just plug those numbers in. So the price equals 400 cents minus 60 cents plus 45. So the price of a 20-inch pizza would be 415 cents, or $4.15. Now for C, suppose the menu had listed a colossal for $6. What do you predict the diameter to be? So what do you have to do? 600 cents equals d squared minus 3d plus 45. d squared minus 3d minus, what do we have here? 555 equals 0. So now you solve that quadratic equation for the two x-intercepts. So plugging this into the quadratic formula, you get d equals 25.106 inches, or negative 22.106 inches. So now we know that we're working in the real world. There's no such thing as a pizza with a negative diameter. So if we have a colossal for $6, the diameter would be approximately 25 inches. Part D, what is the price-intercept of this mathematical model? So the price-intercept is just like the y-intercept. So in this case, what is P when D equals 0? Well, easy to see, that's 45. Now use the discriminant to see if there is a diameter where the price of the pizza equals 0. So the discriminant is b squared minus 4ac. b squared, negative 3 squared is 9, minus 4 times 1 times 45. Okay, so that is negative 90. So what you get is negative 180, isn't it? So that's negative 171. So what do we know? That the solutions in the discriminant, they'd be imaginary if the diameter equals 0. So what do we say? No, there is no, in the real world, there is no place where the price of the pizza equals 0. There's an actual real diameter. And we see the same thing right here. We take a look at the graph. What is, in this case, the price-intercept, which we would used to be called the y-intercept? And we see right there, when x is 0, y is 45. 45 cents. So what does it mean? It means there's overhead cost. So even if you ordered a pizza of even if you ordered a pizza of 0 inches, there's still overhead costs. They would charge you 45 cents. And with the discriminant, you see that it does not intercept the x-axis, so that'd be imaginary numbers. Okay, here's a second problem for you. A rectangular pond, 5 meters by 7 meters, is to be surrounded by a walkway of width x meters. Just as you see it, this problem concerns a rectangular region taken up by the pond and walkway. So write the length and width of the regions as functions of x. Okay, so let's define x as the number of meters wide the strip is. So then the function L of x would be the length that this is, and W for the width of x. So let's say L of x, the length of this, equals 7 plus 2x. Do you see where we get this from? 7 right there, that's the width, but then there's x on this side and x on this side, so that's 2x. Okay. W of x, the width, is 5 plus 2x. And both of these are linear. But now, we're also looking for write the area of the region as a function of x. So area of x equals L of x times W of x, which equals 7 plus 2x times 5 plus 2x, which when we do the math, equals 4x squared plus 24x plus 35. And you see right there, this now is a quadratic function. Okay, part C, predict the area of the region if x is 1, 2, or 3. So a of x when x is 1 equals 1 squared is 1, so 4 plus 24 plus 35, 59 equals, so 63 meters squared. A of 2 and A of 3. 99 meters squared, 143 meters squared. For part D, what is the value of x if the area of the region is 150 meters squared? Well, what do? 150 equals 4x squared plus 24x plus 35. We have to set this equal to 0, right? So 0 equals 4x squared plus 24x minus 115. We plug that into the quadratic formula, and we get x equals 3.144 or negative 9.144, but we're dealing with mathematical models in the real world, so the only valid answer for x is 3.144. Okay, last question. Find the value for x that makes the area of the walkway equal to the area of the pond. Okay, so the area of the pond is 35 meters squared. Do you see that? 5 times 7, 35 meters squared. So then the area of the walkway must also be 35 meters squared. So how do we represent this? So the total then would be 70 meters squared equals 4x squared plus 24x plus 35. Subtract 70 from both sides, 4x squared plus 24x minus 35. X equals? So x equals 1.213 meters or negative 7.213 meters. Negative answers for the real world not included. So if we want the area of the walkway to equal the area of the pond, x equals 1.213 meters. So what did we learn in this lecture? Hopefully you learned something, but just to do a wrap up, we have gone through all of these steps on how to create the quadratic equation, how to use the quadratic formula, how to use the discriminant. Now we're actually getting into using these as mathematical models. I hope you took notes. If you need to, run through this again. We'll do more of this stuff in class. Have a good night.